Okay. Well, for those of you who took exam 2, which is I think all of y'all, the final exam is not going to be any different. It's going to be actually very similar. You're going to have first order RL. You're going to have Thevenin's and Norton's equivalents. It's going to have sinusoidal state and name. So make sure you guys review all those. We are going to cover one problem for each of one of those. So we can get started with whatever I have here, which is sinusoidal state. Okay. Okay. So for sinusoidal state, I didn't see many issues as to the papers that I was grading. With you guys trying to convert these components into their equivalents. What I did see issues in was mainly in dependent sources. So let's work through the problem and I'll touch more based on dependent sources as we go. So of course, this problem is kind of indicative that you kind of have to use name, right? You have two nodes. So we're going to use name, right? So, and in using name, you want to make sure that you use the correct impedance or admittance, right? So name is technically related to conductance, right? So conductance, which in terms of impedance or admittance, you're going to need admittance, right? And that's going to be given by your Y, right? So the three important Y components here is, of course, you have a YR, which is equal to 1 over R, right? Or is equal to G, right? You also have your YC, which is equal to J omega C. And you have your YL, which is 1 over J omega L, or some of you were going off Dr. Russell's document, but it's the same as J over omega L, negative J over omega L. So make sure you have those in mind. Also have these in mind in case it's a mesh problem instead of a name problem. A MAME, of course, deals with resistance. Then focus my hand. Focus.
Really like focusing on your hand.
Yeah, resistance, which deals with, what do you think? Impedance, which is given by Z, right? And then it's basically the inverse of all of this. So for a resistor, ZR is going to be a resistor. CC is going to be the inverse of this. So 1 over J omega C, or negative J over omega C. And then for an inductor, CL is going to be J omega L. So have these two relations in mind when you're approaching a problem like this, because you're going to need it to solve the problem. Okay. So we look at this problem. Also notice whatever the problem is giving you. I saw some of y'all had a good sense of these, but you didn't know what he gave you. So some of y'all took the inverse of conductance and ended back in resistance. So notice here that you have a G, so it's already in conductance, so we don't have to change this to anything. We can just take it. So for this problem, let's name our components, right? So Y1 is going to be G1, which is just 1, right? Y2 is going to be this capacitor here. So it's going to be J omega C. So J omega C2. And our omega is whatever frequency we're operating in. Notice that he also gives you the frequency in the problem, frequency of 1 radian. So I'm going to write over here, omega is equal to 1 radian per second. So our value for this should be J times 1 times 3 farads, which is just 3J. Right. Y3, which is going to be this inductor right here, is going to be 1 over J times omega times L, is going to be 1 over J times 1 times 1. So negative J, right? Y4 is going to be this capacitor. So similar to this one, J times 1 times 0.5, which is just 0.5 J. And this resistor right here at the very end, Y5, is already in G, so it's just 4. Right? So we're going to focus on that one, that one, that one, that one, and that one. Okay. So now that you have your admittances, now you're going to develop your name, right? So your name. Okay, let's start there. So we only have 2 nodes, so this is going to be a 2 by 2 matrix, right? So we're going to look at the first node. We're going to look at everything that is connected to the first node, right? So this guy is connected to the first node, this guy's connected to the first node, and this guy's connected to the first node, right? Nothing else is connected in terms of passive elements, passive or reactive elements. So we're going to have Y1 plus Y2 plus Y3, right? Now we're going to look at anything that's connected in between the two. And the only thing that's connected between VN1 and VN2 is just this guy over here. We're going to have negative Y3, negative Y3. And finally, everything connected to VN2. So this guy, and this guy. So Y3 plus Y4 plus Y5. Close your matrix. This is being multiplied by your nodes, so VN1, VN2. And this has to be equal to your excitations. Okay? So similarly, every excitation connected to node 1. So for current, anything that's flowing into the node is a positive. Anything that's flowing out of the node is a negative. So this JG is flowing into VN1. So it's a positive JG in VN1. This GMV2V4 is flowing into the node. So plus GM V2 plus V4. And now for VN2, this current is flowing out of VN2. So it's going to be a negative GM V2 plus V4. Okay. Any questions so far? Cool. Good. What's up?
Where's the VG? First one.
First column, first row here.
And then, sorry, very far.
Here?
The VG, yeah.
Oh, that's a JG. My bad. Yeah, that's this guy right here. Yeah. Mm-hmm. Okay. So now we have to figure out whatever these two guys are in terms of our node voltages, right? Remember, when you have a dependent source, you're trying to convert it into something that you can work with in your matrix. So we need these two guys in terms of these two guys, right? So let's look at V2, right? V2 is VN1 to ground, so V2 is just going to be VN1. Okay. So I'm going to write it here. V2 is equal to VN1, right? And then V4 is the same thing as just VN2 connected to ground, right? So it's just going to be VN2. So V4 is just going to be VN2. Right? So I noticed this in some of y'all's exams is that sometimes y'all write maybe voltage is equal to current or current is equal to voltage. Just make sure that either you're following Ohm's law equals IR, or that current is equal to current, or that voltage is equal to voltage. As long as you're, sorry, let me show up. As long as you're within these three, you should be fine. You just don't write something that violates any of these three. Okay. So this one's fine because it's voltage is equal to voltage, voltage equal to voltage. So if we plug it in here, I'm actually gonna split this into independent and dependent. I'm gonna have my independent sources, which is just JG and 0. And my dependent ones, just GM. And I'm gonna plug in whatever these guys are. So VN1 plus VN2, negative GM, VN1 plus VN2. Right? So if I was to split this matrix even further into something that looks like this, I would get GM in the first column, GM in the second column, negative GM in the first column, negative GM in the second column. All of that multiplied by VN1 and VN2. Right? So after that, now that this is in terms of VN1, and this is also in terms of VN1 and VN2, this is on the other side of the equation, so I'm going to send this over there. So I'm going to subtract those. So I'm going to subtract this complete matrix from this matrix over here. So after I'm done, let me go to another page. Okay. So if I subtract this minus this, it's going to be y1 plus y2 plus y3 minus GM, right? Negative y3 minus GM, negative y3 minus GM, so that's a plus GM. And then y3 plus y4 plus y5 plus GM would be that last one, right? And all of this is being multiplied by BN1, BN2, and that should be equal to the only thing that we left here, which is just this guy. So JG and 0. Okay. Any questions? Okay. So once you have it in a symbolic form and you have your values here, I would recommend you go to your calculator. And then some of y'all didn't know how to put an I in the calculator. So if you go to this button here, the pi button, you have an I right there that you can use to represent imaginary numbers. Your calculator may trip depending on the settings that you have it in. So I usually have this one in radians. Because sometimes it doesn't solve things if it's in degrees. So I usually like to keep it in radians. So what I like to do sometimes is I like to make variables of these things that I have up here. So I can name a variable y1 and set it equal to 1, right? And then my variable y1 now is equal to 1. So that way I can just put my literally the same matrix in the calculator and calculate it from there. So that's what I'm going to do for all of them. The way you do it, let me do it with y2, is you hit control and you hit this little button right here that has like semicolon and equal sign. So you want to hit that, and then you're going to put whatever value it is. So that was just 3j, so that's 3i. And don't worry about this presentation, it's just the polar representation of that. And then you do that the same thing for y3, which is just negative j. You do the same thing for y4, which is 0.5 j. And then you do the same thing for y5. Y5, which is 4. Cool. Now that I have all my variables in there, I want to type this matrix. And then GM from the problem, it's the only one that we don't know. GM is equal to 2. So we can replace this for a 2 if we wanted to. Or you can make it a variable as well and put it all together. Yep. I'm gonna go ahead and make my matrix. I'm gonna hit this button, go to my matrix. And I'm just gonna ask me how many rows, how many columns. So I want 2 rows, 2 columns. Actually, yeah, that's fine. 2 rows, 2 columns. And I'm gonna type what I have. So I have y1 plus y2 plus y3 minus gm, which is 2. Sorry, out of 5. Then I have negative y3 minus 2, negative y3 plus 2. And I have y3 plus y4 plus y5 plus 2, right? So this is going to be this matrix over here, right? But I want to find v in 1. So what I'm going to need to do, we'll assume is matrix A times matrix B, or times matrix X is equal to B, right? So if I'm trying to find X, X is going to be A inverse times B, right? So what I want to find is this one inverted. So I'm going to raise it to the -1, right? So let me do that again. So to raise it, you use this little button here, raise to the -1. I'm going to multiply by that other matrix over there, which is just 2 row, 1 column. And then whatever value of JG is, and JG is just the value of 5. I didn't touch much on that. Let me touch on that a little bit. When you're changing this into a phasor domain, right? Remember that usually a sinusoidal, we're going to need to change this into a sine representation, right? Sorry, keep it in cosine. Always keep it in cosine. For electrical engineer, we deal in cosines. So usually you're going to see something like this, cosine of omega t plus phi, right? If you change it to its phasor representation, you're going to have jg hat going to be a times e to the negative j e, right? Since this angle is 0 for us, we're just going to have that's equal to a, right? So for us, jg hat is just equal to a, right? So in our case, it's just 5. But in the given case that you had a sign here or you had a face added to it, just make sure you put in this representation. And the calculator will actually take this, so you don't have to change it. You can always just type, I'll show it after I'm done with this, but it would be something like this, if it'll focus and reduce the exposure. So it'll be like a e to the negative j something, or positive j something if the face is negative. Okay, did I do it? So I'm just gonna multiply by 5 and put a 0 here, because that's what my JG is right now. And this is gonna be weird about it. 7. Why is there so many J's here? Oh, yeah. So this is what I was telling you. If you have it in radians, you may see this one.
We can't see it at all.
Yeah. Why is that? Okay.
Hey,
Sure.
are we not able to see the graph or something? Is that what you're doing?
It's no, it's just selecting the whole thing.
Oh.
So wait, what is this not working? Radians, degrees, all of it. Giving me some weird things. Let me check. Oh, that was fine. C. Okay, that may have been an issue. For Y3, I typed negative J. So the calculator was stripping about the values. Let me rename that Y3 just negative I. Now it should work. So now if I just go up and grab that same operation that I did.
Two different.
I just put a J instead of an I. So the calculator is like, well, J is a variable, not an I.
Yeah.
So it tripped up. There you go. So now I have numbers. So this is now in polar. So if you want it in rectangular, you can always do menu, number 2, and number 9. And then here you have two options, convert to polar or rectangular. I want it in rectangular, so I'm gonna put it in a 7. Wait, did I hit the right number? 7. Was not putting in rectangular. Oh. Hmm. Something weird with it. But grab each value. Okay. Well, the calculator is being weird about it, but what I had to do is I had to grab each value, extract it, and do the same thing, just change it into rectangular. So for the second one, I'm gonna get let me just right here. I'm gonna show you all how to extract it as well. So if you have those values in here, you want to select them, and then you want to move through your calculator and just hold shift and then just move to the right until you select all of it, including the E. Then you can use Control C, it's just like a calculator. You can delete all of it and then Control V again, and it will paste that number. And then from there, you can do what I was saying. So menu 2, 9, 7, and it'll give you the rectangular version of that number. So VN1 is, what does that point to?
I'm pretty sure if you had it in a different mode, it would have just put it in the matrix in rectangular.
It usually does it for me. I don't know why it's stripping right now, but yes, usually it works. So for VN1, I get negative 0.2 minus 2.4 J. And for VN1, I get, sorry, VN2, I get negative 0.4 plus 0.8 I, or J. Yep. Yeah.
Like I put them in manually, not adding the values.
Okay.
So it's 1 plus 3 J.
You're missing a plus the minus 2 up there.
What?
And that should be a 2, right?
Oh, I put them on. Okay. So this will be minus 2 up here,
Yeah.
and then at the bottom is plus 2.
Yeah. And without the 4.
Oh, is it
Although
before
that-
the?
Yeah, the 4 is the 5. You're right.
Okay. Yeah.
So yeah, that's what I got.
Okay. So
Cool. Let me just make sure that's correct. Yep, that's correct. Okay, cool. So now, what is the problem asking us for? We're asked to find I3, right? I3 is the current through the inductor. So I'm gonna go back to this equation here, our famous Ohm's law, right? And if I'm trying to find that current, if this thing would focus, okay. So V equals IR. I'm trying to find current, so I'm either gonna have V over R equals I, or V times G equals I, right? Remember that this G is conductance slash admittance. So it could V times Y equals I, right? So I know what its admittance is, right? I know the admittance of that guy. In theory, I just need to find the voltage through that guy, right? So what's the voltage across that inductor? Is Vn1 minus Vn2, right? So I3 of T is going to be equal to that admittance Y3, which is negative J, multiplied by Vn1 minus Vn2, right? And that should be equal to negative J times negative 0.2 minus 2.4 J minus negative 0.4 plus 0.8 J. And then you can put that in the calculator if you want. So it's going to be, make sure you put i's instead of j's, not like me. Minus, let's actually put this guy, minus that guy, I think. Cool. So this is my polar answer. I want this in rectangular. Actually, I think I may want it in polar. Yeah, I want it in polar because I need the amplitude and the phase. So from my polar answer, which is this one, so I got 3.206 e to the negative 3.079 j, right? So going back to what I told y'all about changing it to phasor, basically the amplitude, if it would focus, okay. So basically the amplitude times e to the j phase, right? So if I change this back to time domain, gonna be the amplitude, so 3.206 times the same function, cosine, same magnitude, so t, because magnitude frequency is 1. And then I'm going to subtract the base minus, actually that should be a plus 3.079. Notice that this is in radians. If you wanted it in degrees, you could grab 3.079 multiplied by 180 over pi. And that should give you your degrees. So in degrees, 3.079 times 180, all of that over pi, 176 degrees. 0.414 degrees.
Those both accept words.
Hmm?
Those both accept words.
Yeah, if you let me know, I'll be able to tell. So yeah, they are acceptable.
Do you like care if you write?
As long as you don't get tripped with current, I'm fine. But that's the main reason why we use Jace, because we already have an eye for current. But yeah, that should be the
Doesn't make
correct.
any sense because we also use J for it.
Mhm. Oh, this thing in there. Yep, 3.206. Apparently that angle should be negative. I got a positive 4. Yep, I may have made a mistake, and I think this sign is a negative because of this angle.
Wait, how do I get it in, what do you call it? Bullet format?
Polar.
Yeah.
So
I
let me
think
show
I put
you.
it in right.
So if y'all have it in rectangular form and you want to do it to bullet, you do menu, you do option 2, which is number,
Oh,
and then complex number tools, which is 9, and then you change it to polar. Which is
I
6.
think the reason why you keep getting your answers in polar is because they're probably in polar.
So you have it expressed in literally phasor, so you have magnitude and angle straight
Oh,
up,
okay, gotcha.
and you have it in degrees, so that's even better for you. Mhm.
Oh, no, I'm wrong. B2 and B4.
Yep.
Would it be negative since we're going from positive to negative, like as we go to go along?
No. So remember, voltage has to be measured between 2 points, right? Usually it goes from positive to negative. So these two are going to be, if you measure VN1 minus 0, it's just going to be VN1, right? If this was flipped, then yes. It would be negative VN1. Yeah. It's kind of easier to see with current because usually and most of the time, current would flow that way, right? Unless specified otherwise. So that way you can tell if it's positive or negative. But yeah. So any questions on this problem? No? Straight up, forward. Another nicer problem, which is not really nice. I bet you'll love this one. Okay, let me make sure y'all can see the actual problem. So your usual RL circuit, switching problems that you may or may not like. Okay. So represented with this network, switching problems, what I would recommend is you have 3 stages. Make sure you redraw this circuit 3 times at least. Technically 2, because these 2 are pretty much going to be the same. So let's start with the first one. At time 0 minus, this switch is open, so I can remove this, right? This is not connected to anything, so I can remove it. So I'm just going to have a source here connected to this resistor here with that inductor diagonal and that and that. And I have that connected to that resistor here, so that's going to be a connection to a resistor here. Right? Technically, I have that network. Let me name stuff. So this is R1, this is R2, this is R4, this is R3. And this is your inductor L1. Looks like a 4, but that's an L1. Whatever. Okay. So in the first case, you have T equals 0 minus. That means your network has been sitting there for a good minute, right? How do you model inductors after they've been sitting there for a minute, right? It's just pieces of wire. So it's just going to be a straight up wire through there. So you're going to have that to the resistor. That's just a wire now. Right? Get rid of this. And your task to find the voltage at 0 minus and the current at 0 minus. Right? Okay. This is an L1. I'm sorry. Let me try to do it better. L1. Okay. So from this network, can anybody tell me whatever V0 is going to be? What's the voltage through a short? 0. So V0 minus is going to be equal to 0. We already have an answer. So you can fill 0 here if you want. Right? Now, is my topology going to change because of this short? What do you guys think? Is the way that I should analyze this network going to change because I have this short here? Like, can I remove things because of that short?
Yes.
Yeah. So since this is shorted and current's going to take the path of least resistance, it is never going to go this way, right? So I'm just going to have this and this, right? So I can redraw my network like this. And that resistor, right? And I can slide this wire, this resistor over to this wire, so it's just literally just in parallel. Right? This is 10 milliamps. 10 milliamps. That's our 1, I think, and that's our 3. Right. So now I'm testifying this current, which now became IL0 minus. Correct. So what does this look like? What type of configuration is that? Current divisor. So for current division, multiple ways of doing it. I'll just keep consistent with what I have taught you guys, and is that if you're trying to find this current, I'm going to take the conductance of that one. So IL at 0 minus is going to be equal the conductance for that one over the total conductance times your JG. Right. So in theory, 1 over what is that? So R3 is 4,000. And R1 is 1,000. Multiply that by 10 times 10 to the negative 3, since it's milliamps, right? I'm going to get 2 milliamps.
Going straight into that bare wire, why would it be so much less?
Well, it isn't. It is, but that also, that bare wire is connected to this resistor still. Right? So that's still going to impede the current or reduce the current through it. And notice that this resistor is much, much greater than this one. This one's 4,000, that one's 1,000. So it's going to be 6 milliamps flowing through here.
What was your, sorry, what was your reason why inductor is saying that it's a short circuit?
Inductors, after a long time, act as just a piece of wire because they haven't been charged or anything.
After a long time.
The same way that capacitors, after a long time, act like an open circuit.
Oh.
So we have 2 milliamps here. Now we can change our topology, right, to this. So as soon as the switch closes, our inductor is going to take that value, right, and it's going to start discharging, right? So at t equals 0, plus, right? What does our topology look like? We're going to have this switch close. So now we have to remove this and add this, right? It's going to have this current source, this resistor. Gonna leave that there for right now. That resistor, this voltage source, this resistor, and now, as mentioned, my inductor is now going to act as a source, so it's going to pump current that way. It's going to be that. Okay. It's going to have a value of 2 milliamps. Sure. IL of 0 plus minus 0 plus. So this is our 2, this is our 5, this is our 3, this is our 1. And this is still 10 milliamps. Okay. And this is 20 volts plus. Okay. Is that clear why the inductor grabbed that value and turned it into a source now? Kind of.
Once it closes, would it be an inductor?
Well, yes, but think of, okay. Inductors and capacitors are very similar, right? If you charge up a capacitor, it's going to turn into a hypothetical voltage source and it's going to discharge that very quickly, right? Similarly with inductors, inductors store current, right? So once you charge up an inductor, it's just going to discharge that current once it's stopped being charged. Yep. Okay. So from here, we can grab another value of these. Which one do you guys think? Is it the voltage or is it the current? The current. What's the current going to be?
But it's the same switch.
Yep. Because as soon as it switches, it's just going to keep that value until it's just discharged, right? Okay. So now we're testifying the voltage through there, right? So what do you guys think? You have current source and resistor in parallel. You have a resistor and a battery in series. Technically, two resistors and a battery in series. Source transformations, right? So let's source transform this first, right? Now, if I source transform it, I'm going to have that resistor, that current's pointing up, so my battery is going to be pointing up. It's going to be connected to this resistor. I'm going to have the 20 milliamp source here. Not to scale, but whatever. Sorry. 20 volts. R5, which is 2 point. Sorry, R5, which is 3K. R2, which is 2K. R1, which is, wait, this is R3, 4K. And this is 1K. Okay, so for this transformation, I'm going to just grab the calculator. So it's going to be 10 times 10 to the negative 3. Voltage is equal to current, right? Times resistance, right? So I'm going to multiply that current times the resistance, which is 1000, and I get 10 volts. So this is going to be 10 volts. I'm going to combine the resistors that are in series, right? Because all these two are in series and these two are in series. Even though the battery's in the middle, they're still, you can still combine them in series. You would have that resistor there, that, that resistor there, that. Okay. So 4 plus 1 is 5K. 3 plus 2 is 5K as well. This is 20, and this is 10. Right? And I'm going to finally transform this one last time so that all I have is current sources. So I'm going to have 10 volts over 5,000 ohms, which gives me 2 milliamps. So I'm going to have 2 milliamps there with that 5,000 ohm resistor, with that other source pointing down. So this is 2 milliamps. This is 5K ohms. This is 2 milliamps. This is going to be 5K ohms, and I'm going to have to find whatever this voltage turns into. So 20 over 5,000. 4 milliamps. Okay. So notice that the voltage that we were trying to find is this voltage here, right? The voltage across that. 0 plus. Right. So in theory, if I combine everything and just find the voltage drop through that resistor, it should give me that same voltage, right? Because this is all one node. And voltage in parallel is all the same, right? So all of these guys are seeing the same voltage. Let's go ahead and combine them. Let's see what happens. We have 2 minus 2 minus 4. Is that negative 2? Or negative 4, right? Because these two cancel out, you just have 4. Let me do it in another page. Good job. So just going to have that negative 4 source. And then for the resistors, you're going to have 5 and 5K in parallel. 2.5. If this thing would focus, I would show you how I would calculate it. Okay. So in parallel, 1 over 5,000 plus 1 over 5,000. All of this to the -1. So I get 2,500. So 2.5K ohms, 4 milliamps. And I'm trying to find this voltage, right? V0 plus. So V0 plus. Notice that this current is technically going against this current, right? Because it's being fed up against it. So it's going to be -4 milliamps times the value of that resistor. Right? Which is, I have it here. This guy, negative that guy, times 2,500. Oops, one too many zeros. -10 volts. Okay. So that's another one of our column values. So -10 volts. Right? Now we have to figure out a time goes infinity. Right? So similar case as to when it was just sitting there for a long time. What is the inductor going to change after it has been discharged fully? It has been discharged. This wire. So just a short, right? So what's going to be the voltage through it? The voltage through a short? Right? Because it's been fully discharged. So we can grab this same topology. Actually, let's grab this one since it's already simplified. So t equals infinity. We're going to have that, just a short now. That, and this going down. 2 milliamps, 4 million, 5K, 5K, and then this just a short. So I need to find this current, right? Because we already know the voltage is going to be 0. IL infinity. Right? So what does this tell me? What do you guys think? I can simplify this into just 3 branches, right? If I add these two, I'm going to get -2 or 2 going down, right? Yep. 2 milliamps going down. The parallel combination of these two guys and this short here, right? You get 2 milliamps here. Current assumed to be going that way. AL infinity. And that 2.5K. What do you guys think IL should be or is? Can you explain why?
Because, it shorts out the resistor, right? So it doesn't go through the current between the resistors.
Correct.
Turn off the direction.
Correct. So path of least resistance, or again, it's going to short out the resistor. All the current is going to go up this way. So it's just negative to whatever this is opposed. So it's just L of infinity is just -2 milliamps. Back to our table. We're almost done with our table. We just need tau, and then I'm making the equation for that. Okay. So for your tau, I'm going to give you 2 of them. Tau in an RC circuit, I believe, is equivalent resistance times equivalent capacitance. Tau in an RL circuit, oops, it's equivalent inductance over equivalent resistance. or equivalent conductance times equivalent inductance.
G.
Yes, I'm sorry about my G's looking like sixes, but never been able to fix it. Okay. So we're trying to find equivalent resistance or equivalent conductance for a second. So let's take a look at this section over here, right? I'm going to redraw that one. For sure. I'm going to be analyzing it here. So when you're trying to find tau, you're going to remove the component, the reactive component, and you're going to try to find the equivalent resistance at that point. So for that, you need to turn your sources off. So when you turn your sources off, your voltage source turns into a what? Yep, turns into a short. Your current source turns into an open circuit, right? Luckily for us, we don't have any current sources, so this is just shorted and this is just shorted. So our equivalent resistance is going to be just resistor, resistor, terminal, terminal, and resistor, resistor. All right. So from here, what was this? 1K, 4K, 2K, 4K, 3K. Right? So this is very similar. It's just these two in series, and then paralleled, right? So equivalent resistance is going to be 5K and 5K in parallel, which we ended up already saying that's 2.5K, right? But either I use this here or I use this here, whichever you want. So tau is either going to be whatever the value of that inductor is, which 27 microhenries. So it's either 27 times 10 to the negative 6 over 2.5 times 10 to the third, right? Or you find whatever that is, one number, and then multiply it. It's just the same. Let's just not do that. Let's do that. So 27 times 10 to the negative 6 over 2.5 times 10 to the third. You get 10.8 nanoseconds. Right? And from there, we grab our time domain expression for IL. So time domain expression for IL is going to be given by IL of infinity plus IL of 0 minus IL of infinity times e to the negative t over tau. Right? Out of which we know all of them. So 10.8 nanoseconds. So let's plug it in. So IL infinity is negative 2 milliamps plus IL of 0 is 2 milliamps minus negative 2 milliamps times e to the negative t over 10.8 nanoseconds. Okay. There is part A, B, and we have C at the end, but C should be somewhat simple, I think. Okay. Look at that. I did not look at that last part, to be honest. But I think you just use the equation to find the current. Things like that. Okay. 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 So let me do part B here. I'm still gonna need that equation. I'm gonna go for that. So part C is asking you to find the value of L1, such that the inductor current is 0 at 500 nanoseconds. So that's gonna be your tau, right? So basically we need a tau that's gonna give us 500 nanoseconds at 0. And then we solve it for that. Oh, at time. So we're going to need to find a tau for which your inductor value is 500 nanoseconds at time t equal to 500 nanoseconds, and your current is equal to 0. So t is equal to 0, right? So if we write this equation again, let me simplify it a little bit. So this is going to be plus, right? Oh, the other one. Okay, so I don't need this
Yeah, I
anymore.
was gonna say, let's get rid of that first one.
Yep, since I wrote it down. Okay, so if I simplify that one, we're gonna have IL of t now is -2 plus 4e to the -t over tau, right? So if I have this value and I have this value, I'm gonna have to find a tau that gives me those two, right? I'm gonna have 0 is equal to -2 plus 4e to the -500 times 10 to the -9 over tau, right? Then your calculator, you do -2. First of all, we'll do solve. What's that number? I think 0 is equal to -2 plus 4 times e to the -500 times 10 to the -9 over x. And let's solve for x. Should give me an x. Yep. Gives you a tau of 721.348 nanoseconds. And with this tau, we can now use it in this formula to find whatever our LEQ should be, because we know what our REQ should be. So from tau being equal to LEQ over REQ, right? We now know that tau has to be 721.348 nanoseconds. And that should be equal to LEQ over our REQ, which is 2.5 thousand, 2.5 K ohms, right? So I multiply those two, I should get inductance, right? Should give me an LEQ. So this guy, multiply that guy by 2,500. It gives you an inductive value of 1.80337 millihenries. Oop, you can't see that.
Down to -7.
Oh, because yeah, so this is like the engineering notation, that top one, this one.
Yeah.
But when I select it and copy it down, it just brings it as a decimal rather than engineering. So just, they're the same numbers, just different abbreviations. Mhm. Any questions on this problem?
Wait, what part did you ask again?
So,
Was the towel,
yes, he's asking you for the value that will give you. So the value of an inductor at 1, such that the inductor current is 0 at 500 nanoseconds. Basically that. So you're given time and you're given a current. So with that, you find the tau, which is related to your inductance.
okay.
And then with the tau, you find the inductance because your resistance is not going to change. Mhm. Cool. I also, well, the next one's a name problem. But I remember we did this one by the end of the first review, I think. But if y'all want to do it again, we can do it again.
The other problem that.
Or if you have other problems that you want to work on, that also works.
No, I think he was asking what the other problems in the.
Oh, was that one and Thevenin's equivalent? Whichever you want to do.
What was the last one then? Cause those are 5.
Well, the last one doesn't apply for y'all
Oh.
because y'all didn't get to cover up amps. Unless you want to do up amps, but
No.
you don't want to do up.
Wait, is that topics on the?
Yeah.
And,
Name, Thevenin's and Norton's. First order, either RL or RC, and sinusoidal state. Yep. So
we totally remember how to solve second order even though.
sinusoidal state.
Second order stuff.
No second order.
My differential equation. Yep.
So which one do you guys want to do? You want to do Thevenin's or you want to do name?
I agree with that.
Thevenin, Norton's. This one's Norton's. Thevenin's, I can pull up an example from y'all. This is Norton's, yeah. But it's the same concept. Yeah, yeah. It's the same concept though. I can for sure do one for each. Okay. So for Norton's, here's the basics from what I know. Norton's, it's always related to current and you want to do current? Yeah. Well, you're gonna need current and conductance, yeah. Yeah, I was thinking about what method I wanted to use. So I believe this is May. Right? Because Mave gives you currents with respect to voltages, right?
Yeah.
And then Thevenin's gives you, well, you're gonna need a voltage and a resistance. So you're gonna need to use Nate. Just make sure. Yep. Okay. So let me keep it with it now. Okay. So this is the basics of what you want to do in either of the two problems, right? So the other underlying thing is you're gonna add dummy source. At terminals A and B. right? So this dummy source, depending on which method you're going to use, it's going to be a current source or a voltage source. If you're using main, it's going to be a voltage source. If you're using name, it's going to be a current source. Right? Now, usually when you add them, you want to make sure that they're always positive in your matrix. That way,
You say dummy source, you're talking about the ends, the nodes.
yeah, you're going to add a source here.
I was trying to figure out what you meant by dummy source. I was like, oh,
It's called dummy source because usually it's a value of 1,
yeah.
and you just use it for literally just changing the value, so that way you don't have to do anything, any math involved, but yeah. Okay. So I'm looking for an ordinance, if this thing would focus. Focus, okay. So an ordinance, so I'm gonna use main, right? Since I'm trying to find a current and a conductance. Okay. Cool, main. There's just one single thing that I have to do in this problem for me to use main. And y'all figure it out. Wait. That's one of them. There's another thing that I have to do. Yep. I need to change this dependent current source into a voltage source. So let's redraw the circuit first. This thing would focus.
I'm still surprised that there's not a way to turn off the autofocus.
Yeah, it's a weird camera. I don't even know why. Okay. Voltage plus minus 24. Resistor plus minus. This is going to turn into a resistor. Plus minus. It's fine that way. So I think it's plus minus, but I'll check. Fine. Terminal B. I'm gonna add source here. I'm gonna be my dummy source. I may have to change the polarity in that one because of how my things are. Let me check that polarities right first. Oh, where's it? This polarity is the other way. It's minus plus.
Maybe you could have just looked at the picture.
Yep. Okay. I think everything's right. Okay. So this is a 4K. This is a 1K. This is a 1K. This value is not going to change. Instead of being beta I4, it's going to be beta I4 times the value of that resistance. So 1K. This is going to be a 2K. This is going to be a 2K as well. And this is mu V5. And then I4 is right here. And then V4 or V5 is right here. Okay. And this is what we call the dummy source. So you can call it E0. You're going to have a value of 1 volt.
Now what you're saying about beta.
Yes. So since we changed this into a voltage source, right? We have to do a source transformation for that, right? So it's going to be V equals IR, right? So we need voltage. We have the current, which is given by beta I4. We have the resistance, which is 1K ohm. So that new voltage is going to be beta times I4 times R3, which is just 1000. Okay. So with that, I think we can do. Right. So how many rows of this is going to be? Okay. Everything in the first one, so it's just going to be 4K plus 1K. That 1K is shared between the two, so negative 1K, negative 1K, There's nothing shared between the third one and the first one. Everything in the second one is going to be 1, 2, 4, right? So 1K plus 1K plus 2K. Everything shared between these two is just this guy, negative 2K, negative 2K. And then everything here is just 2K plus 2K. I am 1, I am 2, I am 3. Yep. And then our solutions. So for main, what I like to do is I like to follow the orientation of the currents, usually clockwise. So if I end up in a plus, it's a rise, so it's a positive. So this one ends up in a plus, so that's a positive. So it's going to be, I'm just going to write 24 because I don't know the name of it. This one ends up in a plus as well, so plus mu v5. Right, if I follow it, it ends up in a plus.
Yeah, as it enters the negative exits.
Right, right. It ends in a plus. Yeah, so it exits at a plus, so that's a rise. Now for IM2 though, this one exits as a negative, so it's a drop, negative mu v5. This one's a rise, plus beta times I4 times R3. Right? And then over here, I only have my dummy source, which is negative E0. Right? Because it's a drop. Okay. So now I have to find whatever V5 and I4 are in terms of currents. Right? So V5 is going to be the voltage across that resistor. So again, voltage is equal to current times resistance, right? So what's the current through that resistor? What do you guys think?
V5?
Yeah.
IM3.
Yep. Positive or negative?
Considering it's the wrong orientation of the negative. There is positive. The negative.
So notice the sign orientation, right? In a resistor, it always flows positive to minus, right? So does that arrow go with this arrow?
Oh, yeah.
Then it's positive. So IM3 times R5, which is IM3 times 2K. Right? And now I4 is equal to what? The orientation of this arrow goes with and against which other two arrows?
Yeah.
Yes, so it goes with IM2, it goes against IM3. It's going to be IM2 minus IM3. Right? Okay, let's separate this. So I'm going to have independent ones here. So 24, 0, negative E0 plus mu, which is what? 2 volts.
Yeah. Well, 2 volts per volt, so just 2.
Yeah, so it's 2 times IM3 times 2K. Right? Negative 2 times IM3 times 2K plus beta is 4 times IM2 minus IM3 times 1K. Ran out of space there. And then 0 here. Right. My matrix here, 2 times 2K is 4K IM3. Here, what's going to happen? I'm going to have negative 4K IM3, negative 4K IM3. So I'm going to have 8K. And positive 4K IM2. Right? Kind of weird math here, but I think that's what it simplifies to. Okay. Good. Didn't even do it in numerical. Okay. Let's just go with it. So if I expand this into matrix form, I don't have anything IM1, anything, wait, there's a 0 here. There. Now you see folding. Okay. So I don't have anything for IM1. I don't think anything for IM2. 4K here. I don't think I have, oh yeah, I have nothing for here. 4K here, negative 8K here, and then zeros. 1, 2, 3. Yeah. So as the other one, I'm going to subtract this from this.
So what we could, equivalent to what we had on the, all that.
Yes. So this basically substitutes this, but those two together add up to that. Yes.
And
So you-
24 and then those will say on the right side.
Yeah. The reason why we're doing that is because we have on this side we have a times x, right? On this side we have b. Technically have b plus c times x, right? Because we have b plus c times x, right? So if we're trying to combine them together, we're going to subtract c times x from a times x, and then we're going to solve for that, right? So yeah, so then this is going to be a minus c times x, which is going to be equal to b, and then we solve for b after we subtract the both. Okay, let me move this over here. So let me simplify the numbers. So we're going to have 5K here, negative 1K here, negative 4K here, negative 1K here. 4K minus 4K is 0. And negative 2K minus 8K is plus 8K, so 6K, I think. And 0, negative 2K, and 4K. Oops. IM1, IM2, IM3. 24, 0, negative E0. That's going to be your matrix. I think that's correct.
Replacing that with
Yes, if you want. But the reason I leave it E0 is because of the next step. So now you're tasked to find JG, right? Or JN. Find JN, right? So to find JN, you're going to ask yourself, what current is pertinent for, what current is important for terminals A and B? Current 1, 2, or 3? 3. So you're going to find JN, right? That means you need to find IM3 when E0 is equal to 0, right? So then you're going to have this matrix, 5K, negative 1K, 4K, negative 1K, 0, 6K, 0, 2K, 4K. Okay, let's look at IM2, IM3, 24, 0, 0, right? This is going to give you some 3 values. And the value of IM3 is going to be your JN. Because that's the current that's important for our terminals. Actually, I'll just do it real quick. So 5,000, negative 1,000, 4,000, negative 1,000, 0, 6,000, 0, 1,000, 1,000. 3 by 1. 24, 0, oops. 0, 0. So you get 4 milliamps, negative 1.3 milliamps, and 600 milliamps, I think. 666 milliamps. So then that current is going to be 666 milliamps. So now you need to find GN, right? So GN is also going to be IM3, but when all other sources are 0.
Actively attempting to focus on.
And E not equal to 1. Cool. So I'm not going to write the matrix, but it's going to be this same operation. But instead of 24, I'm going to have a 0 there. And I'm going to have a negative 1 here. So I get IM1 is negative 83 microamps. IM2 is negative 472 microamps. And IM3 is going to be negative 13.889 microamps. Right? So where? Here? 83. Yep. So you can drop the negative and change this to Siemens if you want. Because what's going to happen is you're going to end up dividing by that polarity of that. So GN is going to be equal to your current over your excitation, which is E naught. So it's going to be negative 13.889 microamps over negative 1 volt, which is just 13.889 microsieverts or micro. Oops. Siemens.
I was gonna say that looks like microseconds.
Yeah, that's why I don't like using Siemens. I usually do this inverse ohms. So yeah, so those are your two values, and then you can just, if you want, just put the values there if you want. But as long as you give me that, to me.
Out of curiosity for a step and then Zaldami source would just be 1 amp.
Yes, yes. Usually, so that you don't get negatives down here, I usually make this always positive. So if I wanted to make it positive, the polarity of this would be like this. Right. The polarity doesn't really matter. You just know that you can't have negative resistance or negative conductance. Always just take the value.
So this is that basically the same thing as the resistance across them.
Yeah. Yep.
I'll have to turn on the negative sign. Okay, so it starts at 5 minutes. As a calculation.
Oh, here? Yeah, it should be negative. Maybe that's where I messed up. Yeah. Maybe that's where I messed up because I didn't get what Russell got. That's where I messed up. So, good catch. I forgot these two negatives. That just changes this value to 6 milliamps, 2 milliamps, 1 milliamp. And then if I redo the same thing, 0, tap, tap, tap.
That's
Get
a
one.
big difference in millions.
Whatever. 125, 541.6.7, and 20.833. So it should be that one instead. Get rid of this.
It wasn't that, but
Me.
still
Considerable difference.
Again,
Again,
small it is, yes.
If you show me like all this process, regardless, if you mess up, make a mistake on the math, I'll probably just take like 1 or 2 points. I didn't copy this negative and this negative in this matrix, so I ended up putting positive 4,000, positive 2,000.
So it's coming out as negative 20.832.
Positive out of the calculator is positive, but for GN, just know that it doesn't really matter the polarity. All you really care about is the value. For resistance and conductance,
Because
it's
you
always
divided by the dummy source, so even if you put it correct, it would have just been off.
cool. So yeah, you just show me this process or some variation of it that you understand and it works, and I'll give you credit for it.
This dummy source, it's always going to be a fault and
Yeah,
Yes.
it's one, so it doesn't change the value.
You could make it whatever, but then you would have to divide whatever value you get here by whatever number you put in. There. But yeah. That would be, I do still have that main problem.
Could you treat it as 0 and just have it as
No.
like a short?
No. A 0 is not gonna work, because you need a value.
I figured, but I also had to ask.
Yes, a short is not gonna.
You have a problem? Emergencies?
Maybe?
upload it later.
Yes, I'm gonna upload all of this work to it. Maybe? That hasn't been in your homework? Maybe?
It could even be a homework.
Can be a homework one?
Passing it.
Good.
No idea. Some,
I mean, I think you went over at least one during.
I think I may have done one in the past review. I think I did one. I don't remember if it was Stevens.
You did one on.
Let me check if it was Stevens.
I think you did one of each.
No, it was Norton's as well.
You didn't do. Just one.
I think
We
on
may
the
have just
test,
talked
I
about
think
it.
on the test, it was a feminine problem. So I kind of got.
Yep, just as the other two
I
examples.
was gonna say, I assume it didn't if it worked.
Yeah.
You probably would have said something. about it.
Someone was telling me like there's gonna be like a multiple choice in the beginning.
Yes.
Yeah.
How's that?
So-
He told us that.
So Dr. Russell likes doing a conceptual check.
Yeah.
At the end of your circuits 1. You're gonna have 20 problems, multiple choice. Was it just questions about whatever circuits 1 was?
I think from what he said, that it still counted as being 4 questions or whatever, but the 20 multiple choice count as 1.
Yes.
So the 20 is like each question's worth 1 point, 1%,
I don't know how much percentage of your final
or something like
exam is,
Okay.
but it's between 10 and 20, I think.
each question.
So I think.
He was asking how many points each of
So,
the
yeah.
multiple choice questions were gonna be.
Either 1 or
They'd be a little more than 1, because I think he said there's technically 4 questions. And those count as 1, so they total 25, even if there's only 20.
yeah, so 4 questions in the exam
It would be slightly.
and part A.
Well, that's pretty easy, just like if you're taking those in class, you understand them. type
Yeah.
of
Yeah, he said there.
Response question?
How many?
Yeah.
20, I think.
Who
When I took
responds?
it, it was 20.
Pre-response?
Yeah,
Okay.
oh, wait, pre-response is 4.
Fourth.
Multiple choice 20.
Oh, so then there's 5.
Well,
He did explain it in a weird way. He said there was 4 questions, and then added on the other.
so 4 questions that you have to solve like these.
Four normal questions.
Okay, no, each one is 1.
And then another packet that has 20 questions that are just
Yeah.
multiple choice.
And yeah, so each question is 1 point.
The separate packet is like the packet not open book.
The multiple choice one is an open book. This one is,
They take it at the same time?
no, you take the multiple choice, then you move into this.
No, I meant like the same time frame.
Oh, well, yes, but you first handed out the multiple choice, then you give that one back, and then you hand it out this one.
Still doesn't make any sense why it wouldn't be open, so, because we're kind of technically supposed to open things during it.
Well, not during the multiple choice one.
No, I meant during final exams. You're
Well-
not supposed to dig in your bag.
Yeah, but he also knows if you don't understand it, you don't understand it, you know?
Yeah, fair.
That's one of the topics.
So 7 is an ordinance, sinusoidal state, first order, either RL or RC, and what's the other name or MAME?
Or is the name of the problem?
Are we able to pick up the problem sets?
Yes,
Today?
after I do this ordinance part,
Okay.
unless, hold on, let me just bring the box and you all can.
Because I didn't come by after.
Yeah. So it's having this, it's fine.
Oh, they just went and grabbed
They
them.
moved though, no?
Yeah, if you want them.
I'll be going after I grab it. So-
I believe problem set 4 is on top, problem set 3 is on top. No, midterms are gonna be given out the day of the exam.
Oh.
Let me look for your Northern 7 is from.
Helio.
Mm,
John Wayne? No.
Dylan.
Marcus, ironic, because that's the right first name. Oh. Heck is that?
Yeah. I do have one, but you're not gonna like it,
Okay.
cause it's this one.
Justin Bay. Jonathan.
It's the star.
Where I wrote my name.
Honestly, I wouldn't mind because when I was doing it.
Jacqueline Ostado.
We can do the star. The star is a little nasty, but yeah.
Even though we're using one.
So remember what I wrote, right? 7 is, you need voltage and resistance, you're using MAME. Right?
Then. Well, assuming you don't have any passages or for the finals.
I don't. Those are usually not given out. Wait, this one's 7? This one is 7, but it's source transformation, so that's okay.
Here.
I can find one.
No, those are mine. Yeah. Yeah, there you go.
Just turn it
all the way to
on.
3 above.
It's, if you want, try work out the star one and then send me your work and I can check through it. Let me end this thing.
Do you have any like? There's like study for the multiple choice or?
John,